I'm super excited to be here. We're actually just, you probably saw some of the talks, both from Peter, who talked about deep learning and how to use us a little earlier this week, as well as Jay, who talked about our S-frame and S-array and S-graph architecture. We just came off of sort of a busy week. We had our user conference, our annual user conference down in San Francisco, which this year we had just over 1,000 data scientists and data people. Super exciting. So that's good because it means that I come with a lot of new, fresh demos to share with you guys. So today I'm going to talk to you about us and what we're doing at Dato. So I'm the director of product at Dato, and what's inspiring me is how do we build new experiences, new products that create new businesses ultimately. What are the things that inspire users, other business people, and ultimately the folks in my company? It's all about intelligent applications. So if we look at all of the disruptive companies that are making waves these days, all of them are doing so by using machine learning at the core of what they're doing. And that's pretty different than what we've done in the past with data, which was either to centralize it, provide access to it, maybe make reporting faster. But really now it's all about the apps, the things that we can build using machine learning models. So let's jump right in and talk about one example application, and then we'll sort of dive in and talk about our perspective on things. So this is an experience I think we're all familiar with. Anytime you go looking for something to buy, it all starts with a search. It starts with a keyword. And so let's say that I'm looking to buy my wife a dress. Maybe I'll search for dress. And I get results. So this is basically every consumer experience online today. But the problem is, as a user, I usually don't know what I'm really looking for, right? I know high-level descriptors, but once it gets down to trying to find just the right thing, I'm lost. I don't know how to describe these things. I might know that maybe my wife is looking for a cocktail dress. Okay, and I see lots of different cocktail dresses here, but they're still all very different. I can go a level deeper and say, okay, well, let's filter this. Maybe I want a black cocktail dress. I get some that are black, some that are not. Let's take this guy away. But the problem is there's still many, many different options here. So what are things that we can do to change this sort of standard slow search experience? Well, one is I can teach the user. So if I hover over any product here, I see different words are highlighted. And those words, in this case, are words that are unique to this product. So soutache trim. I have no idea what a soutache trim is, but if I click this, I get other things that are have that kind of trim here. Okay, so that still helps me learn. But it's still not sort of the fast search experience that I'm expecting as a user. I want to get presented objects and then very, very quickly go down to what just matters to me. So let's see how we can do things differently. So let's say that I'm looking for a dress. Maybe I'm looking for something that's floral, but nothing. My wife likes particular things. So let's say I want this one. Okay, so what just happened here is we did a very different kind of search. This is a search based on image similarity. So this completely changes how I find things now. So today we're going to kind of pull away the covers and show how we're making it easy at Dato to build applications like this. In this case, search is kind of worn out. We can do a lot of things with text, and we've kind of done them all. But how do I do more advanced things? How do I do things that are more personalized and more specific to the user? So before we get there, when I think about the process, so here the person data scientist that built this app, and we can talk more about it, is a guy named Trey Kazi, who was a speaker here earlier this weekend. And when he and all of us start our process, it's about going from some inspirational idea, some initial idea that ultimately I want to take and turn into a product that I think is going to change things, the world, my customer's experience, or maybe just how I do things. So the goal is to start from inspiration and to get to production. Anything like image similarity, recommenders, things that require sort of more sophisticated machine learning, I have to figure out how to implement those. I need to figure out how to scale that. Ultimately, I'm usually turning these things into live services, and that's what production is for me. Typically, we start off with prototyping tools, so things like R, scikit-learn, other things that are in the Python ecosystem that you guys are probably super stoked on. And ultimately, when I go to production, I need to figure out how to translate those systems, those initial prototypes, into a deployed production system. And usually that's a different ecosystem, a different set of tools. So in this process, typically we all see the same problem. Sophisticated machine learning is impractical. A lot of the advanced stuff is trapped in papers. And it's also for someone like me, if I rewind, I was a physicist turned data scientist. And so when I got into machine learning, I kind of knew general concepts, and I always knew what I wanted to build, but I didn't know exactly whether or not I needed to use SGD as an optimization method for my recommender, or AdaGrad for my optimization method, right? And most of us, when we start off, we just want an algorithm that's good for a particular task. We want to build a recommender. We want to build a fraud detector. We want to build a search experience. So it's hard to match algorithms to apps. It requires a ton of time and learning. Scaling's costly, particularly for these more advanced algorithms. And then finally, deployment is typically weak. And that's because every time I deploy a new machine learning service, I'm running a bunch of custom code, custom APIs, standing up new web services, and I have no standard way to manage those models once they're in production. So first model into production is hard, but then once I have 100, 500, 1,000 models running in production, how do I keep track of all of those? How do I keep track of versioning? How do I know which of those I need to prioritize and fix to make better? All of this slows all of our creativity down. There's so many more things that we could be building if we got rid of the boring stuff. So who's Dato? We're a company that's been around for a little over 2 years, originally built on an open source project that's about 7 years old. Funded by NEA, Madrona, Opus Capital, and Vulcan, and we're now a little over 45 data folks building all sorts of stuff. We're in Seattle. We're just over in Fremont next to the Troll. And we have one mission, and that mission's to accelerate the creation of intelligent applications. So if you have an idea for a new way of doing search, recommendations, or other customer experiences, we want to make that really, really easy for you, whether you're an experienced data scientist or a developer that's new to the data world. We want to make it easy. So in the last, our products have been out for about 1.5 years, and we're doing well. So these are the folks that are using us now. You can see this is sort of a broad array of folks. So we cover everything from recommenders to multi-channel advertising, to content recommendation, and so on. Just mentioned the Data Science Summit, which was a huge success, a little over 1,000 data scientists, awesome speakers, and there was a lot of hands-on work with us. If you missed that, there'll be videos and tutorials and stuff posted online soon, so stay tuned. Okay, that's sort of enough of the high level. Let's go down super low level and see what it's like as a developer to build and deploy something. And so we're going to build a restaurant recommender here. There we go. Okay, let's fix some of these. Can everyone see this? Is this big enough? Okay, sounds good. Sounds good. I got a thumbs up. Okay, so GraphLab Create is one of our products. We have 3 products. And this is accessed through a Python API. Don't let that fool you, though. We love Python because of the usability. That's why we chose Python as sort of our central API. The underlying architecture is all in C++, and so we're super scalable. We're not instantiating Python objects generally. Okay, so I'm going to go through sort of my standard process that I would regardless of what kind of data product I'm building. In this case, we're going to load some data, we're going to explore it a little, build a model, and then deploy it as a service. And we'll do that in about 5 minutes. So these are restaurant reviews. So the first thing I'm going to do is load these reviews. Let's see. Rest. I need to remind myself what this is called. Let's see. Restaurant reviews, aptly named. Okay. So I'm going to load this into our S-frame, which I don't. How many of you guys heard Jay's talk on S-frames here? 0 people. Sounds good. So S-frame is basically our data frame. We built it inspired in large part to the pandas data frame and our data frame. But what's different about it is it's scalable. That's why there's a big S in front. So it's an out-of-core columnar data structure. So out-of-core means that I can scale to larger than memory. Means if I have a 100 gig data set, even a terabyte data set, I can do that as long as I have enough disk space to fit the data. It's columnar, which means I'm fast for analytics operations and machine learning tasks. This is a data structure built specifically for machine learning. So that's good because it means that you can scale real big, but the API is very similar to pandas, and so it should feel comfortable for you. Okay, so let's take a look at the data, see what we see. So this is sort of the typical Yelp data set. So we have names of places, categories, price range, user ID, rating. There's a whole review here and when it happened. Now, as a data scientist, the standard thing I'd want to do is write a bunch of group by aggregate code, create some histograms so I can understand the shape of my data. We got bored of doing that over and over again, and so we created GraphLab Canvas, which is a simple visualization tool that's part of GraphLab Create. And so here, all of that standard aggregate stuff that I'm always doing just happens automatically. The other thing that's really cool about this is even if my data is really big, I could have 1 billion rows, and I'm going to get results that are really fast, and that's because we do one-pass sketches for all of the statistics that are approximate. And so I see things, these are all for, we built this for the San Francisco conference, so these are a bunch of places in San Francisco. I don't know if any of you have lived down there. If so, you probably would recognize some of these. So Pizzeria Delfina turns out to be the most reviewed restaurant in this data set. And I can learn some other things. For example, the ratings. If I click here, I see that the most common rating is 4 stars followed by 5 stars, and not a whole lot less than that. So we kind of learn immediately that these are highly skewed to be a positive bias, and that star ratings don't kind of tell us that much. Okay, so that's GraphLab Canvas. What we want to do is build a recommender. Why? Because I live in Seattle and I'm going down to San Francisco. I know 1 or 2 places, but I don't know much outside of that. So let's see how that works. So I'm going to take a model, and in GraphLab we have these things called toolkits, which are basically application-oriented bundles of algorithms and utilities to make certain tasks easy. So I'm going to use the recommender toolkit here, and I'm going to pass in the reviews data set. And the only thing I have to specify here is something to make this readable by us. What did I do? Create. Yes, we are creating intelligence, Dato. Okay. So, and I'll talk more about this, but we're trying to streamline everything in this process. So here, I just want something that's going to work right from the get-go, which means I don't want to have to worry whether or not I need a factorization machines with a ranking loss function, matrix factorization with a ranking loss function, item similarity, or if I should predict on rating. I just want to throw the data in, get something that's going to work to start, and then I can iterate later. And so what we do is, based on the shape of the data, we automatically select an algorithm that's going to do a good job to get started. We chose item similarity for this data set, and that's usually a good baseline for recommenders. We see that we had 350,000 observations, so 350,000 ratings here, and then this finished training in less than a second on my laptop. So we're fast. So now that I've trained the model, I can do different tasks with this. So I could do some quantitative stuff. So show me precision recall at K, or I could do some predictive tasks. So predict, given a user item pair, give me a score back. Recommend, given a user, recommend top K back, or get similar items, which is what we're going to do. So let's say that I was in San Francisco and in need of some coffee, and I've heard that this 4-barrel coffee is good stuff. Are there any coffee aficionados in the audience? One. Have you ever been to 4-barrel? Never been to San Francisco. Any coffee aficionados that have been to San Francisco?
I know a coffee aficionado that swears
That swears by Faribault. Okay, good. Okay, so I'll give you some homework to do then. So I've also heard that 4-barrel is very good. What else do I reran that. That's okay. And this has to be a list. Okay, so given 4-barrel, I'm recommended Sight Glass Coffee, Ritual Coffee Roasters, Blue Bottle Coffee. Blue Bottle's recently been making their way up here. If you've seen in PCC, they're starting to sell their New Orleans iced coffee. Coffee Bar, Phil's Coffee, which is a special place, and so on. So it makes sense. And if you do a little digging, you'll see that all of these are artisanal, super fancy, $6 latte places. So that's great. Now I know where else to go waste my money. Let's look at one other example, and then we'll deploy this as a service. Let's say that it's the end of the weekend. The week is just a day away. Let's say that I actually want to look for a dive bar. Let's see, where are we here? Let's just create one more. So I used to live in San Francisco. There's a favorite place of mine there called Amnesia. They have Gypsy Jazz for free every Wednesday nights. You should go. So given Amnesia, I'm recommended Casanova Lounge, Dalva, Elbow Room, Makeout Room, El Rio. These are all dive bars in the Mission in San Francisco. So very different kinds of things I'm looking for, and I can still get good recommendations for both. And we just trained the recommender here while we were sitting and chatting about it. Let's turn it into a service. And we're going to turn it into a fault-tolerant and scalable service. So how do we do that? We have a product called Predictive Services, and I've basically used that to stand up a cluster that's running. You usually just pay that price of 2 lines of code to stand that cluster up once. And then as a team, usually you use this cluster to serve all of your services. You can expand the cluster, but what we're going to do right now is just connect to it and then add this model that we just created. So this is in deploy. And for this one, I need a cheat sheet. Okay, let's get rid of that. Okay, so this is a state path for the predictive service, and that's going to tell me basically what I need to get a handle for this predictive service. So now I have this object called my deployment. Let's take a look at what's running there. So I see here the state paths is an S3 bucket. So this is on AWS. I see that there's 3 machines that are running, and they're all in service. They're all part of this cluster. I see the DNS of the load balancer. So I also know now that there's a load balancer sitting in front of those 3 machines, which is good. That lets me scale easily. And then I see all of the things that I've deployed as a service, and I also see that they're versioned. So this is great. This means that I can keep track of the provenance of a model or a service, and I've connected. So let's actually deploy something. Okay, so to deploy, I can do a number of things. In this case, I'm going to do the most flexible thing, which is just to create a Python function. So I can create any Python function and then deploy that function as a service. So I'm going to create a function called get restaurants, which accepts a name as input. And this is just going to call what we did before. Get similar items, which accepts a list, which is name, and it's going to return that. Return. Okay? So very simple Python function. And then deployment just looks like this. Deployment, add, I'm going to give a name for the service. And so let's call this get rests. And I pass in the function, get restaurants. What did I do here? Oh, there's already a service running. So I could add, in this case I'll update since there's already one there. So update says this is updated to version 2. Use apply changes to deploy all pending changes. So that's good. So let's do that. Apply changes. Okay. All right. So what's happening now, and is basically done, is basically that model that I created here on my laptop with you guys. I loaded that to an S3 bucket. After it's loaded there, each of the nodes in this cluster are notified that there's a new model. You should go pick them up. It's written to each of the nodes. And then in this case, since we're updating instead of a new model, we roll over from the old model to the new model, and the service just stays up. And so in principle, it's up now, and I can query it as a RESTful service. So I could query this with curl, of course, but we also have Python, Java, JavaScript clients for this. So I'm going to query. I give the name of the service, which was get rests, and then I have to specify name equals whatever I'm looking for. Let's say 4-barrel coffee, since we saw those results before. 4-barrel coffee. All right, let's see if this works. So we see that we're connecting to the load balancer, and then I'm given a JSON response back, which is that ranked list of items. If I query this one more time, whoops, I did something stupid. This comes back almost instantaneously, and that's because we have a caching layer. And so for high throughput repeated queries, we're going to be smart about how we serve those. So that means that, in the worst case for simple things like recommend, we're doing 100 millisecond response time. And then for high throughput repeated queries, then we're down in the single digits for a lot of queries. So that's great. We're done. I can directly integrate this with an app. I didn't have to go talk to ops. I didn't have to do something that would typically slow me down. And I definitely didn't have to stand up that whole web service that would have taken, even if I'm good, it probably would have taken a week or 2 weeks to put up, operationalize, and you're not going to have all of the model management that we have here. So that's sort of one example of the end-to-end vision to make things fast, simple, and easy. Any questions? Actually, we're a small enough group that I don't mind stopping for a question or two before moving on. No? Okay. We'll charge through then. So sophisticated machine learning made easy, toolkits. So we saw this here. There's a few principles that are guiding us. we want to make it really easy to get started fast, like the recommender toolkit. And then we want to make it really easy to rapidly iterate. And so that basically means having fast and efficient data structures and all of the mechanics so that you can try out many, many models and improve upon that baseline that you start with. And then finally, we want to make it easy to combine to create new apps that you've never thought of. So this is what we just did, basically. Zoom down. So for recommender toolkit, just a handful of lines of code to create that recommender and get recommendations. And then from here, we'll dive into image search, which was used for the search demo at the beginning. And then our plan as a company is to grow these more and more. So we have around 9 toolkits right now. And we're looking to expand those pretty significantly in the coming year. Our focus is in making these higher level tasks like recommenders, like sentiment analysis, easier for any developer. Okay, something very different. Another way that we can make machine learning very easy is to make feature engineering easier. And one way of doing that is to use something called transfer learning, which is one of the things that Peter covered in his tutorial. So here I'll give you the 5-minute crash course. So the general gist with transfer learning is that I'm going to train a model on one task and then use it for another task. And the way I'm going to use it is basically to extract features. I'm going to use it as part of my feature building pipeline. For images, when we think about an image being processed through a neural net, one image I always have in my mind is this representation of the image, how it changes as I go through each of the layers in a neural net. And there's a couple different things that happen, but a couple of the fundamental ones is if it's a neural net that's been well trained, then as I head down this this representation path, as I get deeper, I have features that are more relevant to the prediction task at hand. And then the second thing is we've also compressed the data. So we've gotten rid of all of the, in principle, we've gotten rid of a lot of the noise, and we've kept only the components that matter for our task. And that turns out to be super useful when we do transfer learning. So this is the simple concept of transfer learning. I start off with something like labeled data, and I train a model to predict those labels. And then I use that model to extract features in new images that weren't part of that set. And then I can create a simpler model, like clustering, like a k-means model, nearest neighbors model, which is what we're going to do, or a classification model, and so on. Okay. So let's see how this works. So to start off, a very, very simple app is just a photo tagging app. And so in this case, we've trained a deep learning model on this very complicated neural net that's very popular. What's the architecture actually called? It is called AlexNet, I thought so, yeah. So this is trained on a topology called AlexNet, which is out of Jeff Hinton's group at Berkeley. It has many, many layers and a lot of different operations in between. But once you, in this case, we've trained it on the ImageNet dataset, which is a little over 1 million images and 1,000 tags. And then we've deployed that as a service, just like we did for the recommender. So that now it's a very simple service. I send a picture, I get labels, and the confidence of those labels back. So in this case, Siamese cat is the label, and this was in the training set, so it's clearly a Siamese cat. Select another image. Goes up, predictions come back, thunder snake, this was a thunder snake. And then let's say I'm looking for something completely different, oscilloscope. This is one of my favorites. So what we're doing right now, this is Getty images being slow. We're just querying Getty images for other images that were not part of the training set. Click on something completely different, see what we get. Oscilloscope. Let's try one other thing. Anyone looking to tag something in the audience? Any objects? We have no human features, but there's 1,000 other things that are interesting. They could be animals. They could be cars. I'll take one suggestion. mountain. I don't know that there's actually like geographic features in here. Let's see what we get. There's actually not, I'm guessing not. Let's see. That looks pretty mountainy. Alp. It has one of the Alps in there, I guess. Okay, so transfer learning. So the idea here is we trained up a model on this data set. It does very well at predicting images that are similar to images in this data set. But what we're going to do is take that model and then use it to extract features for a completely separate task, which is to find similar shoes. So to go along with the dress that I found my wife, I can find her shoes as well. So how's that work? In this case, I'm not going to type, but I'll just walk you through the code. So let's take a look. So we have many different kinds of shoes here. I see sneakers, flats, cowboy boots, all sorts of things, right? There's 6,000 different shoes here. So it's a lot to sift through. Here's how it works. I'm going to load this model, that ImageNet model that we had used for photo tag. And then let's extract features for one image to understand it, and then we'll move on. So in this case, this is an input. I see what it is, and then I'm just going to call .extract features and pass in this image and see what we get back. I get something that's highly meaningful to all of you, I'm sure. So it's basically a big array. It obviously doesn't mean much. We talked about two things that this is doing. One, that these features should have high predictive power, and two, that our data should have been compressed. So let's understand how much the data has been compressed. So I started off with an image which was 256 by 256 by 3 color channels. So let's just look at that length relative to this new length. So I started off with basically 200,000 dimensions, and I've compressed that down to a little over 4,000 dimensions. That's highly useful because it means that I can just directly go and use something like nearest neighbors, and it'll probably give me reasonable results. So let's see. So here I'm going to, we did that for one. I'm not going to make you sit through extracting features for all of these, even though we're pretty fast. We've done that already. And here I'm just going to create a nearest neighbors model where the only features I'm using are those extracted features from deep learning, those deep features. So we'll do this. This is starting and done. So in principle, if this worked, if we have high predictive power in those features, then we'll see search results that are meaningful. So let's say I'm looking for something like this. Hopefully it goes with the cocktail dress that I was looking for. So it's a black heel, obviously. It's very sort of strappy, airy. I don't know how to describe that. But I want to find more things like this. So I'm just going to take the nearest neighbors model, query it for this image, and give me the top K of 10 back. And then the rest of this code is just so that we see it here. Let's see what we get. Okay, so this was the query, and then these are the 9 most similar images in the data set. Seems like it's working. They're all black, they're all high heels, they're all sort of airy, strappy. Let's look at something very different. How about a cowboy boot? So same thing, we're just going to query for this, and let's see what we get. So the next nearest is also a cowboy boot, and then it's followed by other boots that are of similar shape or shade. So that makes sense. We'll do one more, which is, I was at a customer and they wanted to make sure that I wasn't canning all this. And so they said, well, do something else. Okay, so this is a flat. Let's see what we get for things similar to this. So we get, in this case, the dominant thing is not the color, but the shape. So these are all clearly flats. In this case, again, the core intelligence was about taking a model, where were we? Up here, taking a model that was well known to do well for one task, which was classify images into different categories, and then reappropriating it, using it as part of my feature building pipeline to extract features. And it looks like we have good predictive power because I can query 3 very, very different things and get extremely similar things. And that's only using the images. There's no text, there's no tags, there's nothing else that's doing the job of that nearest neighbor search except for those deep features. Super powerful. So at the end of the day, we're all about making it fast for any developer or data scientist to go end to end, take an idea and get it turned into a fault-tolerant predictive service that you can directly integrate with an app and serve the world. People have been using us for a while now, and the bottom line is we're making them all very, very productive. So Baby Center, there's a developer who was originally a DBA, and she decided to build she got inspired to build a recommender. Originally it was a baby name recommender that she wanted to build. And then she found a business use case which was similar, which was basically a content recommender. So a ton of their folks, their site basically serves their community and their revenue comes from ads. And so the more relevant information you give the community, the more they stay on the site and the higher the revenue from ads goes. She was able to, in a hack week, build and deploy her first recommender. And she had no experience in machine learning before this. She had taken a Coursera class on machine learning, like many of us have. And this was her way in. She's now running in production and has moved on to 3 other use cases, including that baby name recommender, actually. She's gone back to that, as well as basically the ability to predict the term that a new mother is in, which is pretty cool. Magazine Louisa, small team of developers, they'd already built a recommender, but they visited us, and they found out that they could basically do the same thing in just about an hour of work with us, and then they've gone on to improve their existing system, make it simpler, but more importantly, replace their recommender with a more accurate and relevant one that's now making them more money. So both of those guys are kind of more on the earlier end of the skills spectrum for machine learning, but for super experienced folks as well, we do well for them. So this is the core research team at Pandora that's responsible for making Pandora's recommendations better. And they're using us because they can iterate faster, they can try more things faster. Similarly, at Living Social, these guys are targeting their users with personalized emails. So you can think about that either as marketing or personalization. And they're using us to iterate faster. And then finally, Glassdoor, they're basically running their job ranking engine on us. And that's through a series of both taking all of the text descriptors of those job recs, creating classifiers to extract tags to describe those jobs, as well as all the way through to feeding that into a real-time ranking engine. Ultimately, these are all just a handful of examples of folks that are extremely productive. They took projects that otherwise would have been 3 months to 6 months and turned them into ones that are weeks instead. So what I talked through here is our platform, which has 3 different products. So GraphLab Create, Jay talked about S-frames and S-graphs. These are our fundamental data structures to make all data manipulation and exploration tasks with machine learning easier. Out-of-core computation, tools specifically for feature engineering, rich data type supports, which means things like you can keep your data as a nested dictionary in an array and directly feed that into an algorithm. You don't have to do this annoying process of going back and forth between dense data and sparse data. Machine learning, we have a lot. I kind of touched on a few key pieces, looking at recommenders, neural nets, and feature extraction for image similarity. We looked at nearest neighbors. We're now upwards of 50 algorithms that are all the most scalable and best implementations that we've known of. And then we use predictive services to take those models and deploy them as services. In the example I gave, we were doing a very simple service, which was just a recommendation service. So give me similar items given this one. But if you remember, I wrote an arbitrary Python function. It is arbitrary. So if you have extra rules that you want to add in, if you want to make calls from 10 different models and then combine them in that function, you can do that. So there's a ton of flexibility in how we've designed that service architecture. And then what I didn't cover today is Dato distributed. So we do distributed machine learning and various distributed tasks. So if you have a complicated pipeline and there's a couple portions that are taking too long, you need them to complete in less than a day or less than an hour, we can parallelize those. And we have a handful of algorithms that do that, but also just a very nice, similarly intuitive API to the predictive service API where I can write a function and then deploy that function across a cluster of machines. So if you want to learn more or just try it out, it's always best to just get your hands on the software and try out yourself. Go to dato.com and download and get coding. Free trial. Works for 30 days, and then you probably talk to me somewhere in there to see what you're doing, what you want to build. My email's here, scully@dato.com, but I hope that you'll go out and help create an intelligent world. And if you want to do that by yourself, I'm happy to give you lots of resources. If you want to do that with us, we're hiring for all sorts of things. So we're 45 folks right now and scrambling to get other awesome people that want to build stuff like this. So with that, I'll call it and take any questions that you guys have.